Hi there. So in this video, we want to talk about doing vectors more with vectors, but we're going to actually use coordinates. So we're going to draw the vectors in the XY plane and use coordinates to do operations. And so let me show you a few things we'll be able to do with that. So in our last video, we would draw vectors if we were needing to add them, but we didn't have a coordinate plane. And so now whenever we get a coordinate plane, we can take advantage of actually using coordinates. So if you think about this vector u right here, if you look at the tip of that vector, it's at the point 3, 5. And so the way we'll denote that vector, we need a different notation for a vector. I'll go through this a little bit more explicitly in a little bit, but we'll use square brackets, or I'm sorry, angled brackets like that. So we'll call that vector 3, 5. Now there's some technicalities here that I'm skirting at the moment, but just to show you. And so then if we look at the vector v, its tip is at negative 5, 4. And so we'll say that that vector has coordinates negative 5, 4, like that. And so then if I wanted to add those two vectors together, okay, all I do is add the coordinates together. And so I have negative 5 plus 3, and then 4 plus 5. And so the coordinates of the sum are going to end up being negative 2, comma 9. Okay, I didn't leave myself enough room in this image, but you could check that by drawing the parallelogram and making sure that that looks like it's in the same place. All right, and just to show you, to do the difference vector, okay, just remember that that really means u plus negative v. All right, and what we'll see in a minute is that to do negative v, I just multiply each one of the coordinates by negative 1 on v. So I have u is 3, 5, and then v, negative v, would be 5, negative 4. I'd multiply each of the coordinates by negative 1. So if I add those x coordinates together, I get 8. And if I add those y coordinates together, I get 1. Okay, now I'm skirting some stuff, and I'm being a little bit quick right now. I'm going to go through this in more detail, but notice that it is a lot easier just to do the actual adding. Now, you got to realize in some problems you're going to be given information about angles and lengths, and so that's where the trigonometry will come in to be able to actually get these coordinates. Sorry, I drew my arrow in the wrong place. To actually get these coordinates, it'll be a little bit trickier. So it is I will tell you, using coordinates does make doing vector operations a little bit easier, but it doesn't completely avoid the trigonometry. Now, another thing I'm about to show you, we can get around it using vector operations. What we'll end up seeing is that vectors can allow us to do some geometry problems that would be very complicated from the trigonometry standpoint. And so say I was asked, I just gave you the picture of this parallelogram, and I tell you to find its area, all right, like that. Well, this is actually a pretty complicated problem because all I know is the coordinates of the vertices, like that this is 1, 1, and that this is 8, 2, etc., etc. Okay, so to do this problem, to find the area of this triangle, it's actually a pretty complicated problem without vectors. Okay, that what you end up doing is you draw this diagonal, and you can use the distance formula to get the length of this line right here from the coordinates. You could get the length of this line from the coordinates, and you could get the length of this dotted line using the coordinates and the distance formula. And so that gives you a side angle side triangle, and so you can use the law of cosines to find this angle. All right, and then once you know that angle, you'll know this length right here, you'll know this length and this angle, and that included angle. And so there's a formula for the area of a triangle using a side angle side relationship. Okay, that, you know, it's not terribly difficult, but you know, if you remember the law of cosines, to find an angle is a pretty complicated calculation in and of itself. And then also getting those side lengths. What we'll see is once we know how to use vectors better, okay, and learn some operations with vectors, that all we'll have to do is form the vector going from this point to this point. Let me change that color because it's not showing up very well. Well, that's even worse, isn't it? All right, let's go to blue. Okay, form the vector going from that point to that point. Form the vector going from this point to this point. It's not drawing. There we go. like that, and then we'll compute what's called the cross product of those two vectors, and we'll be able to use that cross product to get the answer with only a couple quick calculations and no trigonometry whatsoever. So yeah, let's get started on how to do all this. All right, now this is going to seem a little bit obvious, but there's going to be a little bit of confusion about when we use parentheses and when we use angled brackets. But the basic idea is that if I have some vector, so remember, think about the last video, that here I just have a vector. I've drawn it. It has some length and some direction, right? Like that. So what we do is we imagine drawing this in the coordinate plane. Now, what's important right now is that right here, that I need to set things up so the tail is at the origin. Okay, so if I were going to draw in axes right here, I'd want to draw them right here. Well, that's a horrible axis, isn't it? I'm going to do it in a different color too. Okay, so I'm going to draw it where it's in the coordinate plane now. But to do what I'm about to show you, it's important that the tail be at the origin. Okay, like that. And so then what I do is I find the coordinates of the tip. So I imagine, you know, counting out like that. All right, like that. And then then I look at the coordinates of the tip. Now here's a very subtle point. The coordinates of the tip is a point. Okay, we're at that point right there. All right, so right here, this would be about 4, 5. So the coordinates of that point, the white part, is the point 4, 5. Okay, but the vector, the coordinates of the vector are the angle bracket 4, 5. Okay, sometimes it's important to distinguish between the point and the vector. There's some situations where we don't really distinguish between them. So you just got to be a little bit careful about the context of what you're working on. But the subtle difference is a point is just a location. Okay, it just tells you where something is. But a vector is an actual physical quantity with magnitude and direction. All right, and so these are actually different things. They're highly related to each other, but they are completely different things in terms of interpretation, and that's the reason we use the different notation. Okay, and so the coordinates of the vector are angled brackets 4, 5. The coordinates of that white point, though, are parentheses 4, 5. All right, and so then a natural question is, what if there's going to be situations where you need to draw a vector where the tail is not at the origin? So how would I get the coordinates there? And so let's get some axes up here. All right, and so here's our axes. All right, and let's say I have a vector that starts here at the point 2, 3, and then comes over here to the point 6, 5. So here's my vector right here. But if you remember, to get the coordinates of this vector, I can move it around. All right, a vector is only determined by its magnitude and its direction. So what can I do? I can go and I can move this thing down, move it to the origin. I just got to make sure and move it correctly back to the origin. So what do I need to do here? Okay, I just need to take this point and move it back to the origin, but then I need to make sure this point ends up in the same location so that it has the same magnitude and direction, in the correct location, I should say. Okay, so what's the idea here is that this right here is going to be the origin now, and what does this vector need to do? It needs to go to the right a certain number of places, and then it needs to go up a certain number of places. All right, and if right now we can count those tick marks, we'll talk about how to compute them in a minute, but I went to the right by 4 units, and then I went up by 2 units. And so now whenever I redraw this vector starting at the origin, I just need to make sure it does the same thing. So it needs to go to the right 4 units, and then it needs to go up by 2 units. And so here's the same vector, just drawn with its tail at the origin. And now since the tail is at the origin, I can say what the coordinates of that vector are. They're the vector 4, 2. Okay, now think about this. You've seen this. I mean, this little diagram right here shows up in so many places. The distance formula, the slope formula, and so on. And so instead of having to draw that and count the tick marks, how can I get those numbers just by looking at the vector? Well, if you think about this, this original vector started at the point 2, 3, and then its tip is at the point 6, 5, right? Like that. So to get that 4, what did I essentially do? I subtracted the coordinate of the tip minus the coordinate of the tail, the x coordinates. And then to get this 2, I subtracted the y coordinate of the tip, and I did minus the y coordinate of the tail. Like that. Okay? And so what we're trying to get at here is that if I have a vector that starts at x naught comma y naught and ends at x1 comma y1, like that, then it has coordinates. I subtract. Now you got to be careful about the order here. The order is important. I do the coordinate of the tip minus the coordinate of the tail in the x's, and then same thing in the y's. Okay, and so people will use a phrase here to try to keep that in mind. They'll say the tip minus the tail. All right, just be careful. You got to remember that there's two coordinates there. But you know, some people that are visual just do draw it out and then do it that way. But this is a nice formula to keep in mind. So you got to remember that, though. If I have a vector that's starting at one point and going to another point here, okay, the coordinates of that vector aren't just the coordinates of the tip, okay? They're only the coordinates of the tip whenever the vector is drawn starting at the origin. If you want to get the coordinates of this vector right here, you take the x coordinate of the tip minus the x coordinate of the tail. That ends up giving you your first coordinate. And then you do the y coordinate of the tip minus the y coordinate of the tail. That gives you your second coordinate. Now, like I mentioned, a lot of practical problems come where we're just given the magnitude and some angle, okay? And so how do we get the coordinates in that case? So let's look at a picture similar to what I put in the previous video. So say I have a horizontal and I have a vector v here. And I tell you that this angle right here is, let's just say 34 degrees. And this is the vector v. And I also give you that the length of v is 10 units, okay? Like that. All right. Now, and see, that's the thing. In practical problems, you can set up the coordinates the way you need to. Okay. And so what I can do is I can redraw this in the XY plane, and it would be pretty intuitive that you would want the origin to be right here because you want the tail at the origin. All right. And so we're going to redraw this in the coordinate plane. All right. And so I'm going to come here and draw myself an XY axis. That vector is 10. Okay, so since I have that vector drawn with its tail at the origin, all I need are these two coordinates right here. I need the coordinates of that point right there. All right, and once I get the coordinates of that point, that'll be the coordinates of the vector. Well, here's where some trigonometry comes into play, is that I can drop my vertical line right there, and so that forms a right angle, right? And so what I really have right here is a right triangle. All right, this is 34 degrees. All right, and this is 10. You got to be a little bit careful. A is the x coordinate, okay? So as far as A goes, A is the x coordinate, so it's this length right here. So A is right here in this picture, okay? Like that, and then B is the y coordinate, the vertical displacement, and so B is right here in this picture. Okay, now you got to solve for A and B separately. You don't get them at the same time, but think about let's focus on A right now. Okay, so in terms of finding A is, first of all, notice 10 is the hypotenuse in that triangle. Okay, B is the opposite side, and A is the adjacent side, like that. Okay, and so what can we say about A trigonometrically? We can say that the cosine of 34 degrees is equal to A over 10, like that, and you go and isolate A, you'll end up with A is 10 times the cosine of 34 degrees. Don't worry so much about the decimal approximation now. Okay, and then coming over to B, B is the opposite side, so it's going to pertain to the sine. All right, and so we get sine of 34 degrees is equal to B over 10, like that. Multiply both sides by 10 to isolate B. We're going to get 10 sine of 34 degrees, like that. All right, and so what all is that saying now? That's saying that the coordinates of my vector, V, its x-coordinate is 10 cosine 34 degrees, and its y-coordinate is 10 sine 34 degrees, like that. Okay, now one important thing here, you don't even necessarily need to go through this trig here after the next slide that I show you. The important thing here is notice that this angle is drawn where it starts on the positive x-axis and goes toward the vector. That's called a standard position vector. Okay, and if a standard position angle. And anytime you have your vector drawn and the angle is in standard position, you actually get this you get this expression right here. All right, and I'll summarize that on the next slide. Okay, so if I have a vector and I know its length and its angle, the angle that I know is in standard position. Now you got to be careful with that. I'm going to show you this with the next example. Not all angles are given in standard position, but you can always compute the angle from the standard position. Okay, but if you know the length of the vector and you know the standard position angle, we'll call it theta, all right, then we can automatically jump to the coordinates of V. It's just the length of V times the cosine of theta, and then the y-coordinate is the length of V, the sine of theta. All right, so let me show you a situation you might have. All right, and so let's say the length of V is equal to 15, okay, and but then I draw a picture. All right, and so let's say I draw this picture. Here's a horizontal, okay, and so here's V right here. But in these kind of pictures, it's it's often easier to give this angle right here straight from the horizontal. Okay, so now I want to go and I want to draw this in the XY plane now. Okay, so V would be coming over here. Its length is 15, and then this angle right here is 64 degrees. Now you have two ways to handle this to get the coordinates of this thing. Okay, you can draw this right triangle right here, like that, and go from there. All right, the problem is with a right triangle, everything's going to come out positive, and you got to remember you're over here on the left side of the x-axis. So you'll have to remember to make x negative, okay? Or we can get the standard position angle. The standard position angle always starts on the positive x-axis and rotates to the vector, okay? So there's our angle theta that we're talking about up above here, all right? And so how do we get theta? Well, the theta and the 64 form a straight angle. So, you can either write it out, theta plus 64 is equal to 180 degrees. Some of you know just to subtract from 180, but however you get it, theta is equal to 116 degrees. Okay, and so now, since theta is in standard position, we can just jump straight to this formula here to get the coordinates of V instead of going through all that trigonometry. All right, and so we would have 15 cosine of 116 degrees and 15 sine of 116 degrees. Okay, like that. And you could approximate them. If this were the answer to the problem, then yeah, feel free to go ahead and get the decimal approximation, and so like that. But if you're going to use this in a problem, usually we're like adding vectors or doing some kind of operation. If you're doing that, you want to keep this exact and use this as your vector, and then only start approximating at the end when you actually need the answer in approximate form. Now let's talk about how to find the magnitude of the vector whenever we have coordinates. Okay, so let's just look at a concrete example. So say V is the vector 2, 4. Okay, and I want to find the length of that vector. Okay, so we go and we draw this. So here's here's the tip of that vector. So here's my vector right here, and what I want to find is I want to find how long that vector is. Okay, like that. And so just like with working with the angles here, we can always go back and draw this triangle right here. Okay, and so this length right here is 2, and this length, the height right there is 4. We have a right triangle, and we're trying to find the hypotenuse, and so we would just use the Pythagorean theorem there, that the length of v squared, that's the square of the hypotenuse, all right, is equal to 2 squared plus 4 squared, all right, and so the length of v squared is going to be 4 plus 16, which would be 20, like that, and so then the length of v is going to be the square root of 20. Hopefully you know how to simplify that. That's 2 square roots of 5, like that. Okay, like that. And so in general then, if a vector has coordinates v1 and v2, we would do the same thing. We would still draw this picture. It's just those side lengths here would be v1 and v2, but we could go through the Pythagorean theorem. But then the length of the vector is going to be the square root of, I square each coordinate and add them together. All right, like that. And so getting the length of a vector is pretty straightforward. All right, now once you have coordinates though, the operations are actually easy in coordinates, okay? And so remember, there's the idea of a scalar multiple, okay, like that. And so you're going to have c times some vector, all right? C is a scalar, and so just imagine, let's just use general coordinates for v. So it's just going to have a first coordinate and a second coordinate, like that, all right? And the nice thing is, whenever you have coordinates, you basically just have, you just basically distribute that c into the vector. Now I will tell you, so very often we go just the opposite way. We have a vector right here where we started here, and we see that we have a common factor. Sometimes we factor that out, all right, to make especially in an answer, to make it look a little cleaner. Okay, now this is one of the most amazing things in the world to me, in the math world to me, adding. Okay, so say I have u plus v, like this. I showed you at the beginning. So say u has coordinates u1 and u2, and v has coordinates v1 and v2, like that. Now you are going to say, why, what's so amazing about this? But whenever you're adding vectors in coordinates, you do just add the corresponding coordinates. So you add the x coordinates together, and then you add the y coordinates together. Can you think about why that is amazing to me? Think back to that last video, okay? To do u plus v, we had to draw that parallelogram and then go through that all that trigonometry to get the length of that vector, and then we had to use law of sines and law of cosines to get angles and put everything back together. And amazingly, this is just amazing to me, that all that trigonometry in coordinates just gets boiled down to just adding coordinates together. It's just an amazing fact to me that that all this intense trigonometry is just boiled down to just adding coordinates together once you have coordinates. All right, and then make sure you realize subtracting, oops, wrong color, subtracting just combines the two together, okay? And so if you have u minus v, then that's going to be u plus negative v, okay, like that. So what's negative going to be? Negative v is going to be negative 1 times v. So what are we going to have here? We're going to have u1 comma u2, and then plus negative v, it's going to be negative v1 comma negative v2, like that. All right, and so what am I going to get here? I'm going to abbreviate this, but I'm going to have u1 plus negative v1, but that's just a subtraction. All right, and so whenever you're subtracting vectors, you just subtract corresponding coordinates, like that. So the operations are actually very straightforward once you have coordinates. All right, so here's just some basic examples and make sure we have those. So let's say u is the vector 5, -8, and v is the vector 3, 6. All right, so we're just going to practice doing these operations. I would advise pausing right now and just going through and making sure you have it down. There are subtle little things that people make silly mistakes on. So just call this free practice, pause it and try them, and then go ahead and pick back up with playing. But anyway, so for 2u, we have 2 times the vector 5, -8. So I just distribute that 2 in there, and so I get 10, -16. The vector 2, 10, -16. Okay, for 1/3 v, same kind of idea, but we're working with v, so we have 1/3 times 3, 6. All right, and so I distribute that 1/3 in there, and the 1/3 times 3 is 1. 1/3 times 6 is 2, so I just get the vector 1, 2. Okay, so let's see, let's separate all these so it's easier to see. Okay, and so then u plus v, I add corresponding coordinates, and so I have the x coordinate would be 5 plus 3, the y coordinate would be -8 plus 6, like that. And again, it's so easy, but every time I do it, I just get a little bit amazed about how that shortcuts that whole parallelogram law thing. Now be careful, we still will have to do trig. I'm going to show you what's leading into a practical problem right after this. Okay, and so and then u minus v, I subtract coordinates, so I have 5 minus 3 and -8 minus 6, so I get the vector 2, -14. All right, like that. And then 2u plus 1/3 v. Now, one thing I could do is I could compute 2u, and then I could compute 1/3 v, and then add them together. Make sure you realize that's problems 1 and 2, though. Okay, so we already know what 2u is. It's 10, -16. And then I add that to 1/3 v, and that was 1, 2. So then if I add the x coordinates together, I get 11. If I add the y coordinates together, I get -14. Okay, so 6 is similar. Problem 6 here is similar, except that I don't already have 2u and 3v computed. So first I need to compute 2u. I'm sorry, I said that backwards. 2v. We're going to be careful here. We're doing 2v minus 3u. So I need to multiply the coordinates of v times 2. And so I get 6, 12. And then I'm subtracting. I need to multiply the coordinates of u times 3. That's going to be 15, -24, right? And so I get 15, -24. All right, and be a little bit careful with that subtraction. So I have 6 minus 15, and then I have 12 minus -24. All right, so those two are going to create a plus right there, is what I was telling you to be careful about. So easy to make that silly mistake there. All right, and so what do we get here? -9, and then comma, +36. All right, so now let's look at a problem where we're given magnitudes and angles and add stuff, add and subtract. Okay, so let's look at a problem like we saw in the last video and do this with coordinates though. So say I'm given these two vectors, length of u is 8, length of v is 6 feet, and the directions are pictured. So the u has an angle to the right from the horizontal of 26 degrees. V goes to the left from the horizontal up 71 degrees. Okay, and so what we're going to do here, we're going to do this slightly different instead of going to the parallelogram law. And what you want to do is you just want to find a method that you like better, and for these types of problems right here. And I'm not going to tell you ever that you have to do it one way or the other. All right, so anyway, I'm going to show you this. So we want to get the coordinates of u and v. But to get coordinates, we need a coordinate plane. Okay, so we need to draw in coordinates. I think it's pretty obvious where you would want to draw them here. So I'm going to draw my axes right here. Oops. Got to get it on there, though. All right, so there's my x and y axis. All right, and so notice for u, its angle is drawn in standard position. It goes from the positive x-axis. Okay, and so for u, its length is 8. So I would say 8 cosine 26 degrees, and then 8 sine 26 degrees, like that. Okay, and then for v, its angle's not in standard position. Okay, so we need the standard position angle. Standard position angle starts at the positive x-axis and comes around to there. So hopefully you see that that's 109 degrees. All right, and so for V, its length is 6, so I get 6 cosine of 109 degrees, 6 sine of 109 degrees, like that. All right, and so now the adding and subtracting are easy. I have U is equal to, U plus V is equal to 8 cosine 26 degrees plus 6 cosine of 109 degrees and 8 sine of 26 degrees plus 6 sine of 109 degrees. So there's the coordinates of U plus V. U minus V is going to be the exact same thing, except there will be minuses there. Okay, so the only thing that happens is you end up subtracting those. So that's easy. And so you're saying, why would we even talk about that whole complicated parallelogram law thing? Okay, what's the problem here? If I stopped here, if I said that was the answer, okay, that I didn't answer this problem in the format that it came. Okay, the format of the problem gave lengths and angles, and so I need to answer this in terms of what the length of each one of these is and what the angle of each one of those are. Okay, and so that's where the trig's going to come back in and some slightly complicated calculations. All right, and so first of all, I forgot to put something in the direction. So let's just say, let's give answers to 2 decimal places. Sorry, I'm being a little bit sloppy too. So give answers to 2 decimal places. Now we got to be a little bit careful here. We don't want to compute these 2 things and round those to 2 decimal places. All right, so what we want to do is we want to compute each one of these numbers here and store them. All right, and so that's going to be the key thing, because the answers to this problem are the lengths of each one of these vectors and their angle from the horizontal. Okay, so what I just did is I just typed in each one of these. So I typed in 8 cosine 26 plus 6 cosine 109, and then I stored that to the letter A. So this is my letter A. Okay, what I did is I took advantage of some calculator features and I brought up the previous line and I just changed this plus to a minus and I stored that in the letter C. What I'm getting at here, what I'm trying to get to is I'm going to store this as B, this is C, and this is D. So however you do that. All right, so the key thing is you want to type, the calculator I'm using won't store an entire vector, so I have to compute each one of these parts. I'm just using my regular graphing calculator right now. And so however you do that. So I'm going to store each one of those numbers as a separate variable. So if you want to get an idea about what they are, it's always good to have an idea. So A is about 5.4 and B is about 9.18. And then C is about 9.14. And D is about negative 2.17. But what you definitely don't want to do is use those numbers to do your calculations. Have them stored so that your calculator is saving several more digits. Okay? All right. So so then for the length of U plus V, remember what I do. It's the square root. I square each coordinate, so it's going to be A squared plus B squared, and then I add the coordinates together. All right, and so now this is part of the answer, and so I will be able to write it rounded to 2 places. So I have A squared. I'm just typing in the square root of A squared plus B squared on my calculator. Like that, and that's about, to 2 decimal places, that's about 10.57. Now this problem has units in it, so that's 10.57 feet. Okay, and then for U minus V, the length of U minus V, then I would just type in the square root of C squared plus D squared. Okay, and that's what I'm doing right now. I'm just typing in square root C squared plus d squared. Uh-oh, I messed up though. Where's my d? Oh. Okay, and so that's about, that actually rounds to 9.40. Okay, like that. So we have the lengths of each one of them, and now we need their angles. I'm going to have to go to the next slide, though. Okay, and now see, this is going to be a case where these approximates help us, because we need these angles. Okay, so for u plus, and we got to remember, we're doing these separately. These are two different answers. Okay, so for u plus v, we need its angle from the horizontal. So let's draw it from these coordinates right here, these approximate coordinates. So u plus v, x coordinate is about 5.2 far, and y coordinate is about 9.18. So it comes out, I'm just going to kind of rough it in here. Okay, but the key thing is its x coordinate is about 5.24. That's not exact. Okay, and its y coordinate is about 9.18. So you can see that its angle goes up above the horizontal, all right, like that, and we need that angle right there. So what are we looking for? We're looking for this angle right here, and so we think about having a right triangle, all right. Its base is about 5.24. Now remember, I have that stored more accurately in A, okay, and then its y coordinate is B, which is about 9.18, and I'm looking for this angle right here. Well, this side's the opposite side, this side's the adjacent side, so the tangent of theta is equal to B over A, okay, like that, and so theta is equal to the inverse tangent of B over A, like that. And so if I type that in, I'm just typing in inverse tangent of B divided by A, I get about 60.30 degrees. Okay, so again, like in the last lecture, one way to answer this problem is just to draw it. Okay, it's about 60.30 degrees. So this is u plus v. Its length is about 10.57, and its angle is about 60.30 degrees. What did I forget on this part? That's feet. All right, so there's the answer. There's the first half of the answer right there. Okay, and then for u minus v, like that, then now we got to be a little bit careful here. So for its picture, its x coordinate is 9, but its y coordinate is -2. So u minus v goes below the horizontal. Okay, like that. And so, but we can give that angle from the horizontal. Going down, that negative just means that that length is -2.17. But remember, that's d, all right? And then this is c right here. And we're looking for this angle right here. And so that angle there is going to be the inverse tangent. You know, draw it out if you need to. Here's your right triangle. This side is D. This side is C. You got to be careful because sometimes the opposite and the adjacent reverse around in your picture. Okay, but this is the opposite side and this is the adjacent side. Okay, so we're going to get the inverse tangent of D over C. All right, and so I'm just typing that in again. D over C, like that, and that's about 13.32 degrees. Now, if you practice that, it's actually giving me -3.32 degrees, okay? But remember, what we're doing is specifying angles from the horizontal, and we're answering with a picture. It might depend if you're seeing this in another class. It might, your instructor might want you to draw it slightly different, okay? But the idea here is that u minus v goes like this. It's a lot more flat though. Like that. Its length is approximately 9.40 feet, and then its angle is tilted below the horizontal at about 13.32 degrees. Okay, and that's one way to answer that problem. Okay, so so you can see there's always going to be the trig. It's a little bit more basic whenever you use whenever you use coordinates. But just the key thing is remember if you're given a problem that starts with angles and magnitudes, you don't want to stop here. You want to answer in that same format. I forgot to circle my answer. That's bugging me. Or I did circle it, just in the wrong color. All right, and so you want to answer it in the format that the problem came. All right, but you can see things are a little bit simpler, and notice that, you know, the way that the coordinates work out, if you draw that, it'll tell you. Remember, we had that issue in the last video of not being able to tell if this vector was above or below the horizontal and having to do extra work, but the coordinates will present that kind of stuff to you. So using coordinates does help you a lot. It's just that you got to remember, you don't stop here if your problem started with magnitudes and angles. All right, so there's going to be a second part to this with some more specific information about vectors, but these are the basics of using coordinates. They are very helpful, and so hopefully that makes sense. Let me know if you have any questions, and all the best.